Our topic today is wax mitigation and remediation, a microfluidic approach. Jelaine has been with Interface for several years now. She is currently a senior account manager, providing technical insights to the business development team and matching customers with their ideal product. She also has experience working in Interface's lab and with core flooding and a background in chemical technology.
Perfect. Thanks so much for the intro, Lee. So today I'm going to talk to you a little bit about Interface's approach to testing wax appearance temperature, as well as some of the other ways that we approach the wax problem. So before I begin, I'll start with a few slides on the background to this problem, how it impacts the oil and gas industry, some different approaches for mitigation and prevention of this problem, and then go into Interface's specific offerings. So to begin with a little bit of background, as we know, flow assurance is very critical for oil production. So one of the most important aspects of flow assurance is to ensure the safe and efficient transport of hydrocarbon crudes from underground reservoirs to surface facilities. The deposition of wax within the reservoir and on conduit surfaces is a primary cause of production losses. Because of the delayed productivity and the costs associated with wax remediation, this has actually been estimated to cost the industry billions of dollars annually. One source even stated that this problem can cost up to $330 billion per year when factoring in the environmental impacts that wax can have when things like spills are considered. So extracting waxy crude oils from the oil field is a time-consuming and it's often plagued with certain difficulties. So a number of crude oils have a considerable amount of waxes, also known as paraffins. When temperature and pressure are reduced during oil flow, the oil structure is destabilized, which increases its viscosity and also can result in wax precipitating in the well tubulars and pipelines. So common problems that are caused by this wax deposition include reduced production due to decreased flow rates, increased power required to run pumps, equipment failures, choking of flow lines, well shut-ins, premature abandonment. The list goes on and on. So of course, given all of those challenges, it's very important that we prevent wax deposition, and if it is to happen, that we're able to remove it. So there are 4 main wax inhibition and removal methods, including thermal, mechanical, chemical, and biological. Each of these come with their own kind of advantages and disadvantages. But what we'll focus on today, and is something that Interface typically focuses on, is the chemical side. So chemical techniques have shown to have the greatest popularity in recent years. And some of the advantages of using chemistry for wax treatment is that it doesn't interrupt the production. There's long distance pipeline compatibility and reduced restart pressure and yield stress. So chemicals are able to actually inhibit or prevent this by altering the properties of the wax, decreasing the viscosity, pour point, and wax appearance temperatures. So chemistry is, of course, a broad topic as well, and there are a number of different chemistry based techniques for both the mitigation and remediation of these waxes. And the benefit of working with Interface is we're able to actually help you match the right chemistry based on your challenge or your application. So when it comes to mitigation, often different chemistries like crystal modifiers are used, which help to delay the precipitation of irreversible waxes and enable the removal of wax aggregates by oil flow. They also help prevent the agglomeration of these waxes. There's also different chemistries like drag reducers, and I see a number of chemistry experts on the call, so I'm sure they can help give you a little bit more information on those as well. But there's also different chemistries like nanoparticles, which help to alter the viscoelastic networks and improve flow characteristics. On the removal side, Chemistries like dispersants are used to break up wax particles so that the production flow can carry them. And often chemistries like solvents are used as well for wax removal. One of the benefits of chemistry is that they can be used alone or in combination. And depending on the application at hand, getting the right balance is really important. So, of course, I touched on this already, but there are a few gaps between solving wax problems with chemistry. First of all, there's no one chemistry that, at least that we're aware of, that can be used for all wax problems. Chemistry is not always cheap, so it's important that you have the right dosage so that you can do what you need to do without spending too much. Often specialized chemistries are used based on a specific problem, and then that problem needs to be tested. So it's important to have accurate reservoir conditions or pipeline condition testing before choosing a chemistry. So interface's solution to wax. Interface Fluidics uses our WAP methodology based on our in-house microfluidic technology. So microfluidics is the study and the manipulation of fluids at the picoliter to microliter scale. And at Interface, we use our combined expertise in oil and gas engineering and microfluidics to create a unique suite of tools to address wax challenges. Typically with our microfluidics, we're using different microscope. Oh my goodness. We're using different techniques to visualize these challenges. But for wax, we're using cross-polar microscopy. So with cross-polar microscopy, wax crystals appear brighter than the background, as you can see in these three images here. So this method allows wax appearance temperature measurements to be done at high pressure, potentially high temperatures as well if needed. And it gives us a really accurate measurement for when the wax appears. So now I'll walk you through our testing protocol. So the first thing we do at Interface is we fabricate specific reservoir analogs based on the reservoir or the process that we are replicating in the laboratory. The microfluidic analog is then mounted on our custom manifolds, and these manifolds are what allow us to go up to reservoir relevant temperatures and pressures. So we then raise the manifold temperature to the starting conditions, and then we inject several pore volumes of the oil into the analog. To measure the wax appearance temperature, the chip temperature is dropped at a rate of about 1 degree Celsius per minute, and then that is even further refined once we're approaching the wax appearance temperature. So the test ends once we see those wax crystals under the cross-polar microscopy. There's a number of different advantages to this technique. Firstly, it's very highly sensitive. We're able to see even the smallest particles when they appear. And we're able to get a lot of visual information that we don't get in other techniques. It's also pretty fast, so we're able to do these measurements in less than a day, and they require a very, very small amount of oil. So with the reduced time and the reduced amount of oil, we can screen through a range of different chemistries really quickly. And the picture on the bottom left there is actually one of our devices that we use for this testing. So now I'm going to walk you through a case study that we recently did with one of our clients who was having a wax problem. So we had a client who was dealing with some wax stabilized emulsions in the production line that were causing issues at the separator. Chemistry was already applied when they came to us, but the costs were very high and the mechanisms were unclear. So what we were able to do was help this client optimize their chemical program, which was previously challenging due to lack of information that they had. So our goal was to analyze the different wax modifiers, look at the mechanism, and understand the performance of these different chemistries. We also wanted to look at emulsion characterization and provide the client with a workflow for chemistry selection that could be scaled and repeated. So what we did was we screened 3 different chemistries, both on their own and in combination. In the first group of tests, we analyzed the impact on the wax appearance temperature, the wax deposition, and the crystal growth. And in the second set of tests, we examined the emulsion size, the number of droplets, and the flow characteristics. So again, in this case where we're looking at the wax appearance temperature, what we had was the temperature starting at 80 degrees Celsius, which was reduced gradually until we started to see the onset of the wax crystals. So right now I'm playing a video actually, which is showing the wax deposition for both the control case, where you can see a number of these crystals depositing, and then for the 2 chemistries. So what we saw was that the control had the largest amount of wax deposited and the highest degree of wax growth. Chemical 2 showed the smallest amount of wax deposited and a 27% reduction in the wax appearance temperature, compared with only a 2% reduction for chemistry number 1. Both of the chemicals prevented wax crystal agglomeration, but chemistry 2, again, had the highest percentage of small size particles, which demonstrated its effect of dispersing the small wax crystals. So we can see in these charts on the bottom, they're showing a number of different things. The chart on the far left is showing the relative wax coverage as the temperature is decreased. So you can see the blue line there is the control, and it has a significantly larger amount of wax coverage compared to both chemical 1 and 2. And then on the far right side, what we're looking at is the distribution of the particle size, with chemistry 2 and chemistry 1 having a higher frequency of smaller particles. So then when we moved on to the second part of this study, which was looking at these wax stabilized emulsions, what we observed was that in the control run, many small emulsions were apparent, and these small emulsions were surrounded by wax particles that made this emulsion very stable. When we added chemistry A, we saw mostly slug flow with a minimal amount of emulsions, and the droplet size was considerably larger. With chemistry B, we saw both slug flow and large size emulsions. And then using chemistry C, again, both slug flow and emulsions were observed. Although improvements were observed in emulsion size for chemistry C, there were still more small-sized emulsions compared to chemistry B. So what our goal here was to evaluate, the impact on the slug flow and this droplet size, which would help select the chemistry for field use. So in addition to wax appearance temperature, there's a number of different measurements that Interface Fluidics has commercially developed or under development. So currently we offer a number of different phase behaviors testing that is fully commercial, including asphaltene onset pressure. We can also look at minimum miscibility pressure and diffusion measurements. And then currently Interface Fluidics is working in a joint industry project with ExxonMobil, Equinor, Enhance Energy, and another multinational company to develop what we're calling the PVT lab of the future. So all of these measurements that you see in gray on this slide, we plan to have fully commercial next year. So those measurements include what we call an enhanced CCE. So anything from your gas oil ratio, dew point, bubble point, liquid vapor ratio. We're also looking at commercializing live oil viscosity and live oil density, as well as swelling factors. In addition to this set of PVT testing, Interface is also looking towards the future at deploying hardware. So this is what we call Sapphire Lab, and it's a small, safe, and repeatable bench where we're actually able to deploy our microfluidics testing to your lab. So this platform is multifunctional. It's high pressure, high temperature compatible. It includes the same high resolution optical measurements that we do in-house. And it's able to perform all of the measurements that we just talked about. So things like wax appearance temperature and wax inhibitor screening. So with that, I will wrap up this webinar. But we talked about wax now. It's a billion-dollar problem, and it's very important to be mitigated. And what we do here at Interface is we help you evaluate different methods to ensure that you choose the right chemistry for your application. Interface can fill in these gaps while providing safety, convenience, speed, lower cost, and using lower volumes. So with that, I'll open it up to questions.
Well, thank you, Jolene. It looks like we do have a few questions in the Q&A here. So the first one, is there a method to test wax deposition removal by solvents in pipeline systems?
Yes, so I did touch on that. Oh, maybe I didn't touch on that. But yes, we can use solvents to investigate wax deposition. It's something that we've done in the past, and we've also done it for the purposes of destabilizing asphaltenes, for example, and looking at that impact. So with our platform, we're really not limited based on the type of chemistry. So solvent investigation is definitely something we can do.
Great. Do you work with live oil?
Yes, so we also do live oil testing. That's an option for each of the different tests we use, and we don't require very much of it.
What temperature ranges can Interface work with?
So we can go up to about 220 degrees Celsius or over 400 degrees Fahrenheit. And then for waxes, often going below 4 degrees Celsius as well.
Here's another one. What sample sizes are available for wax deposition testing? And can we accept oil samples that have passed through a wax deposition event?
Yeah, so typically we don't require, our actual testing only requires 0.1 milliliter. Typically we take, about 50 milliliter samples from our clients to ensure that we have representative field samples, and then we can perform a number of subsampling and testing on that. And yes, we can accept samples that have already gone through this. We like to take actual oil field samples. So in that case today I went through, that oil was that was oil that had already gone through one of those events.
Great. Can Interface use field wax solids to do testing?
This question I'm not sure. I would have to have a little bit more information. Typically we don't do a lot of work with solids, so I would have to know a little bit more for that one. So if you can reach out to us, you can either reach out to me directly, jolene.f@interfacefluidics.com, or you can reach out to the contact on the webinar information. We'd be happy to follow up.
Okay. How is reservoir pressure reflected in microfluidic testing?
So for this question, I'm just going to, so the testing that we do is very similar to conventional core flooding or other equipment where we bring the equipment up to high pressures. So we're able to go up to 15,000 PSI. So provided your reservoir is within that range, we can match those reservoir pressures.
All right. And has Interface's methods been verified against benchmark data?
Yes. So all of the methods that we've developed with Microfluidics have been compared against conventional laboratory measurements. And we don't commercialize any testing that we don't view as good or better than conventional testing.
How do wax appearance temperature results compare to DSC?
So we've done some comparisons, and we're within a few percent of conventional DSC testing. That said, based on our visual access and our high resolution, we believe we're able to very accurately detect the onset.